Yeah, welcome back to our next lecture on digital signal processing. Today our topic is frequency domain representation of signals and systems. Already you know about myself, Dr. K. Manikanta, assistant professor from the Department of ECE. Today we will discuss about what is frequency domain and how it is represented when you are giving signal to the system. So for this, I'm considering an LTI system. Already you know about that linear time invariant system. Linear time invariant system means it is not changing with respect to the time. So I am giving an x of n as an input signal. This is an input signal, and I am getting an output signal is y of n, and the response of the system I am considering as a h of n, nothing but y of n equals to h of n. So for for analyzing the frequency domain representation of a discrete time signals and systems, I am considering one LTI system, and I am giving an input signal x of n, and I am getting a response for that x of n is here called as the impulse response h of n, that is a output signal y of n. So for this h of n, I am finding the frequency response. The frequency response of a is represented by h of omega, or it is also can be represented by h of e power j omega. We can represent the frequency response either h of omega or h of e power j omega, since the frequency response is nothing but the Fourier transform of the signal. The Fourier transform is nothing but the signal which from time domain to the frequency domain. As it is a discrete time signal processing, here again to conversion of Fourier transform into omega. That's why I'm taking h of n is changing with respect to h of omega by applying the Fourier transform. So while getting the response of the system, we know about that convolution property. Already we have discussed this convolution property. So what is convolution property? Nothing but y of n equals to, I am saying that the response y of n is equals to h of n. In the system, we are getting y of n equals to h of n. So the total response, I recall the response of the LTI system for the to the input signal x of can be written as y of n equals to the convolution of x of n with the h of n, or h of n with the convolution of x of n. So like this, we will consider the convolution of these two responses is nothing but the total response of an LTI system. So what is the formula of convolution? Y of n is equals to summation k equals to minus infinity to infinity h of n into x of n minus k. This is the formula for the convolution of any two signals, h of n into x of n minus k. So by using this property, we'll know the frequency domain representation of a signal and system. So if for this, actually you are saying that here I am giving an x of n as the input signal, and I have concluded that y of n is the convolution of these two signals. This is the procedure. So now I am assuming that I am giving a signal x of n is equals to some x signal. So that signal here I am considering a system with a complex exponential. I am taking a complex exponential signal. X of n is equals to what? A e power j omega n for the interval of minus infinity to infinity, and omega is the minus pi to pi. So here I am taking a real example called x of n equals to a into e power j omega n, and I am checking for the output y of n. How? Already we know that the output y of n is the convolution of x of n and h of n. So if you see here, y of n equals to convolution of x of n with respect to h of n. Yes or no? Now we have to check y of n equals to x of n is nothing but what you are considering, a into e power j omega n into h of n. This is the convolution. So by applying the convolution formula, what you will get, y of n is equals to, see here, if you see here, this is the property, summation k equals to minus infinity to infinity h of n into x of n minus k. So by applying this, sorry, here this is h of k, not h of n. If you see here, h of k into, in place of x of n, we have a into e power j omega n. Means n is replaced by n minus k. So what will happen? A into e power j omega n minus k. Because what you are getting here, x of n minus k. Here x of n is what? X of n equals to a into e power j omega n. And x of n minus k means this x of n signal is delayed by the kth delay. Then what will happen? X of n is replaced by n minus k. That is why a power j omega n minus k. That's why you wrote like this: x of h of k into a into e power j omega n minus k. So coming to here, this is a constant, arbitrary constant. I am taking this one at the outside of the summation. A into summation k equals to minus infinity to infinity h of k e power minus j omega k into e power j omega n. How it came means, here I wrote a into e power j omega n minus k. So this can be written as a into, 1 minute. Here e power j omega n minus k is the arbitrary constant, already you taken left out of the box. So if you take e power j omega n minus k, this can be written as e power j omega a minus b is nothing but e power j omega a into e power minus j omega k. Means I am taking the multiplication of these two, e power j omega n into e power minus j omega k. So because of this, all the signal is the summation with respect to k. That's why I am considering this e power minus j omega k inside the summation and e power j omega n outside the summation. So a into e power j omega n, this is called as a frequency response of the signal, that is denoted by h of omega. This is in the form of summation k equals to minus infinity to infinity h of k into e power minus j omega k. So already I have told that previously, h of omega or h of e power j omega is the frequency response of the system. So that's why h of e power j omega is called the frequency response of the system. And here for finding the frequency response, we need two terms, that is magnitude and phase of the system. Magnitude and phase of the system. And whatever the signal we got here, e power minus j omega k, whatever the signal summation k equals to minus infinity to infinity h of k e power minus j omega k, which is consist of real part and imaginary part. Real part and imaginary part. For obtaining the frequency response from this equation, we have to know what is the real part of the equation and what is the imaginary part of the equation. Here h r of e power j omega. This h of omega is the what is the h r omega? It is a combination of real part and imaginary part, and this can be described as like this: h r is the real part of h of omega and e power j omega, plus j into the imaginary part is represented by I e power j omega. So now the magnitude and phase can be, for this equation, it can be represented as, the magnitude can be represented as modulus of h of e power j omega. Already we know elementary one. This is the elementary condition, you know. H of e power j omega, modulus is nothing but a magnitude of the system. And if you want a theta, means e power j angle of h of e power omega or e power j omega. You can consider j omega, e power j omega, or else you can also consider h of omega. So this is the magnitude and phase. Then next, in the next slide, we will see what is the formulas for those. Here h of e power j omega is called the frequency response of the system, and the real part and the imaginary part of the system, already you know that. What is the magnitude response? How the magnitude response will come? Means the magnitude response is nothing but h of e power j omega equals to, here what is the real part? Suppose h of omega equals to 2 plus 3i. Suppose if in case the response of the system is like this, then what is the magnitude of this system? Means the magnitude of the system is nothing but what? The real part square, h r e power j omega whole square. Here the what is the real part? 2. So 2 square plus what is hi e power j omega whole square, nothing but imaginary part square. 2 square plus what is the imaginary part? Doesn't consider I, it is a imaginary part indication, so 3 square. So what is the magnitude now? Root of 2 square plus 3 square means 4 plus 12, but the magnitude is equal to, sorry, 4 plus 9, 3 square, 2 square is 4, this is nothing but root 30. So this is the magnitude response for the signal. Similarly, what is the phase response? The phase response is denoted by, here the magnitude response, as I said earlier, it is represented by modulus form, and the signal is represented by angle of h of e power j omega for the phase response. And if you see here, angle of h of e power j omega is nothing but tan inverse of what? 2 plus 3i means hi, imaginary term by real term. What is the imaginary term? 3. What is the real term? 3 by 2. So this is the phase response, and you can calculate by using calculator tan inverse of 3 by 2. Then we will get the phase response. Like this, we will find the frequency domain representation. So coming to the starting slide, what is the frequency response? Is nothing but giving the signal, we are getting output. The frequency response can be done by using a theorem or a formula called convolution, and by using this convolution we are getting the signal, and then we are representing that with respect to, we will see the problems also on this same topic. For this, I am considering, for knowing, I am taking a first order system and second order system. And for these two systems, I am deriving a frequency response of or frequency domain representation of the system. So for that, first I am considering a first order system. So if you see here, the first order system having a transfer function h of z equals to 1 minus a z inverse. So what is the first order difference equation? Is nothing but y of n equals to x of n minus a into x of n minus 1, or you can take as a1 also. If it is second order, minus a2 x of n minus 2. So it's first order system. By applying the Z transform, we will get y of z equals to x of z minus a1 into z power minus 1 x of z. So by commoning y of z equals to x of z, by commoning x of z, we will get 1 minus a1 into z inverse. So from here, we can write h of z is nothing but the output by input equation. So we will get the h of z equals to 1 by 1 minus a z inverse. So for obtaining the frequency response of any system, we have to apply convolution theorem, and we have to consider z equals to e power j omega. We have to substitute z equals to e power j omega. So if you see here, in the place of z, I am substituting e power j omega. Then what will happen? H of e power j omega is equals to 1 by 1 minus a into z power minus 1, means z is e power j omega, and by multiplying j omega with minus 1, it is a power minus j omega. So from here, we have to know the imaginary term and the real term for finding the magnitude and phase response of the system. So if you see here, I am taking this e power minus j omega. E power minus j omega can be written as, by using Euclid formula identity, cos omega minus j sin omega. So see here, I am substituting in place of e power minus j omega, I am substituting a cos omega. So what will happen? So 1 by 1 minus a into cos omega minus j sin omega. So in the place of e power minus j omega, I am substituting cos omega minus j sin omega. So from this, I am separating the real and imaginary term. So what will happen? 1 by 1 minus a cos omega. This is the real term. Minus into minus, this is the plus, j into sin omega. So this is the imaginary part, and this is the real part. So now we got the real part and imaginary part. As said earlier, the magnitude response is the square root of real part square plus imaginary part square, and phase response is nothing but tan inverse of imaginary by real. So from here, what is the real part? 1 minus a cos omega, and what is the imaginary part? Sin omega. So coming to this here, h of e power j omega. Here it is representing modulus, means nothing but a magnitude response. If you coming to here, 1 by root of 1 minus, why it is in the form of division, so that is why 1 by root of what is the imaginary real part square? 1 minus a cos omega whole square, plus what is the imaginary part? A sin omega. So a sin omega whole square. So next one is phase. Phase is nothing but minus tan inverse of imaginary by real. Imaginary term is a sin omega by 1 minus a cos omega. Like this, we can derive for any order number of the system the frequency response. If you coming to the here, what you are seeing, first order system and second order system. Now we will check for the second order system. Nothing but we will consider another one, minus a2 into x of n minus 2. So for that, the transfer function is equals to 1 by 1 minus a1 z inverse minus a2 z power minus 2. So similarly, for obtaining the frequency response, you have to substitute z equals to e power j omega. So I am also here also I am substituting h of a equals to 1 minus a1 into e power minus j omega minus a2 into e power minus j omega is multiplying with 2, so 2j omega. So by using Euclid identity, you can write as e power minus j omega is cos omega minus j sin omega, e power minus j 2 omega is cos 2 omega minus j sin 2 omega. So here if you see 1 minus a1 into, in the place of e power minus j omega, I am substituting a cos omega minus j sin omega. So multiplying a1 inside a minus a1. So see here, I am substituting 1 minus a1 cos omega minus j sin omega minus a2 into cos 2 omega minus j sin 2 omega. So what I am saying that 1 by 1 minus, I am multiplying this a1 inside the brackets. So a1 cos omega minus a1 j sin omega. So similarly minus a2 cos 2 omega minus a2 j sin 2 omega. We got this point. Just I am multiplying these things. So after that, I am separating the real part and imaginary part from these two. So if you see here, what is the real part? 1 is the real part. Minus a1 cos omega is the real part. And minus a1 j means it is a imaginary part. So you leave it. Minus a2 cos omega, minus a2 cos 2 omega. This is the what part? Real part. Now you will see the imaginary part, plus j into, so what is the imaginary part? Minus a1 sin omega. So I think here you can take this one is minus a1 minus a2, not plus, because you are get sorry here we will get by multiplying this a minus 1 we will get minus, so that's why this one also plus. So j a1 cos sin omega plus a2 sin 2 omega. So we got the same equation now. H of e power j omega is the real part and this is the imaginary part. Okay, for obtaining the phase response, you have to calculate the magnitude for obtaining the frequency response, you have to calculate the magnitude response and phase response. For that, magnitude response is nothing but what? The root of real square plus imaginary square, and nothing but phase response is the tan inverse of imaginary part by real part. Here the real part is this one and the imaginary part is this one. Now we will calculate the magnitude response h of e power j omega. It is denoted by modulus of the h of e power j omega, 1 by root of real square plus imaginary square. And similarly, the phase response h of e power j omega is nothing but minus tan inverse of what is this? Imaginary by real term. The imaginary term is nothing but a1 sin omega plus a2 sin 2 omega by 1 minus a1 cos omega minus a2 cos 2 omega. Like this, we can calculate for any type of or any order of the difference equation. So what is the procedure you are following? Just we are keeping z equals to e power j omega in the given transfer function, and later what you are doing, we are applying the Euclid identity, that is e power j theta equals to cos theta plus j sin theta, or else you can also write as e power minus j theta equals to cos theta minus j sin theta. So by substituting these two Euclid identities, we are separating the real terms and imaginary terms. So from these real and imaginary terms, we are finding the magnitude response and phase response. The combination of those two is nothing but a frequency response of the system. So like this, we are following the frequency domain representation of a signals and systems, where x of n is the signal, y of n is the response, and it is the what is that y of n is nothing but the convolution of x of n with the impulse response. Thank you. This is our lecture today.